Yeah, he's talking about the environment playing a role in quenching low mass galaxies in the protocluster. So please start.
Thank you. Hi everyone, my name is Richard Pan. I'm a PhD student at Tufts University and I work with Danilo Marcassini. And today I'm actually going to be talking about my recent paper on is environment playing a role in quenching low mass galaxies in a protocluster at redshift 2.6. And so to begin, I want to talk about this image on the conference page of Abell 2744, which is a low redshift galaxy cluster characterized by a hot X-ray medium, intercluster medium, and a high fraction of passive red quiescent galaxies. And what we've seen in clusters is that this hot ICM is efficient at environmentally quenching low mass galaxies in these clusters, and that thereby will build up the red sequence in clusters. And we see this with common environmental quenching, such as ram pressure stripping or galaxy starvation, which we've seen this week so far. But today I want to ask the question, is this also true in protoclusters, or progenitors of galaxy clusters, in which their environments, they're not quite virialized, they're not as hot or as dense as our low redshift clusters? Can these environments still efficiently quench low mass galaxies, especially at cosmic noon? And so first, I'll need to talk about two surveys that really enabled this study to happen that I was a key contributor for these past few years. The first one is Uncover, which actually took this image of Abell 2744, where we leveraged the lensing magnification of this cluster to really reach unprecedented depths. Depths that allow us to detect faint, low surface brightness galaxies, such as low mass quiescent galaxies at cosmic noon. And then the second survey is the medium band megascience survey, in which we were able to take this broadband SED from Uncover, fill it in with all the NIRCam medium bands, and able to accurately constrain and robustly measure the photometric redshifts of these galaxies. And so my main contribution for Uncover and megascience was to actually try and detect the faint background sources in this field. And so what I had to do was model the brightest cluster galaxies and the intracluster light and remove them as such, which I know some people might not like. A lot of people are interested in that, but for our research purposes, we were looking for background sources that were faint, and we wanted to make sure that we had reliable photometry. And so with this, we have deep data from Uncover, we have reliable photometry after removing the foreground light, and we have accurate photoz's from the medium bands. And so what we can do now is look for redshifts, look for protoclusters in redshift space. And so what I've shown here is a redshift histogram centered around cosmic noon above this mass limit, and on the top panel, you'll see all the galaxies above this mass limit. And on the bottom panel, you'll see all the spectroscopically confirmed galaxies. And what might immediately stand out to you is that there's a significant peak right around redshift 2.58, which we've called the overdensity and highlighted in red. And then in purple, it's the higher and lower redshift field bits, so that we can compare our overdensity sample to the field sample. And now we've heard a lot this week of just what is a protocluster, how do you define it? And one way that we're going to do it is to look at the dark matter halo mass of our system. And to do this, we look at the stellar mass halo mass relation from Baruzzi et al. 2019 to infer that our dark matter halo mass was roughly around 10 to the 13.2 solar masses or 10 to the 13.6 solar masses, depending on if you use spectroscopically confirmed galaxies or just all the galaxies. And so this is actually in line with a lot of common redshift 2 protoclusters, such as the spiderweb protocluster. And so now we can put our overdensity into this relation from Muldrew, Hatch, and Cook, where on the x-axis you see the redshift 0 galaxy cluster dark matter halo mass, and on the y-axis you see the redshift 2 protocluster halo mass. And what you see is that our overdensity is in a pretty reasonable range for being a redshift 0 galaxy cluster. And so we determined that our overdensity was a likely protocluster. And so now, lastly, we need to look for quiescent galaxies. And to do this, we use the star-forming main sequence shown here on this black line, and we've selected all galaxies that fall half a dex below this line as quiescent galaxies, totaling 34 quiescent galaxies in the protocluster and 29 in the field. And now, most other studies to date would probably try to answer the question of, is there a role of environmental quenching by looking at their quenched populations? And they would ask the question, are there more quiescent galaxies in the protocluster as compared to the field. And the naive assumption is that the quiescent galaxies in these denser environments would still be forming stars in a lower density environment. And so to do this, we compare the quiescent fraction, which are the fraction of all galaxies that are quenched. And on this plot, we show our study and see that at the low mass head, this might be true. The protocluster sample has a 2 sigma significance higher quiescent fraction than the field. And so naively, we would say, oh, there's a role of environmental quenching. The environment has to be turned on to drive up these numbers. But if we correct for field variations, and we look instead at the quiescent fraction excess, we see that our sample is actually not that significant. In fact, there's only about 10% of these galaxies that are quenched by their environment, and it puts it in line with other similar studies at similar redshift and other simulations. And so what's unique about our sample is, yes, we did probe the low mass regime for the first time, thereby making this discovery a little novel, but what our sample is really uniquely capable of doing with the well-sampled SEDs is actually look at their stellar populations and ask maybe a more intriguing question, are these quiescent galaxies forming and quenching on similar timescales to the field? And so the assumption here, again, is that quiescent galaxies in this dense environment would have their star formation truncated, leading to a discrepancy in their stellar populations when compared to the field. And so to answer this question, I'm going to compare their formation time and their quenching time, which is roughly speaking the time it took to form 50% of its stellar mass and 90% of its stellar mass, respectively. And what you see here on the plot is that our protocluster sample in red is highly overlapping with the field sample. And when we do a KS test to try to compare these two quantities, we see that the p-values are greater than 0.05. And so we can't reject the null hypothesis that, in fact, the protocluster sample is pulled from the same sample, same population as the field sample. And now when I take the difference between the formation time and the quenching time to get the star formation time scale, this roughly correlates to how long it took to form the bulk of its stellar mass, the galaxy's stellar mass. And so we've heard from earlier this week that when galaxies undergo, for example, ram pressure stripping, they might have burst-year star formation. And so you would expect, naively, that the star formation timescale would be narrower, would be shorter than the field. But what we actually see is that, again, they overlap significantly with the field when we correct for redshift variations. And we see that there's actually no significant difference between the protocluster and the field. But one thing that the KS test doesn't really show with these numbers is that it doesn't account for the uncertainty on our measurements, uncertainties that we've painstakingly measured. And so to do this, we want to model the population distributions using Bayesian population modeling. And what we do is we take the uncertainties, we try to find the likelihood population distributions of each of these samples, the formation time, the quenching time, the star formation time scale for the protocluster and the field for each stellar mass. And what we find is that there's high overlap between the two, around 90% for all of these quantities, indicating that there really is no difference between the protocluster sample and the field sample. Now, lastly, we can look at their star formation histories and try to compare the two because we would want to see a difference between them. But when we stack them up and we put them side by side, we see that they're actually pretty much the same. Here we've normalized the star formation history given the different total masses, and we find that, again, within 1 sigma, there's really no difference. And so our conclusion here is that there actually is no significant differences between these two populations. And so the conclusion is, well, this protocluster environment that we found, our redshift 2.6, is not environmentally quenching these low mass galaxies efficiently. And we saw this with the low quiescent fraction, we saw this with the similar star formation timescales, formation time, quenching time, as well as the similar star formation history shapes. And what this means ultimately is that our protocluster quiescent galaxy sample is likely being quenched in a similar manner as the field sample, and most likely being due to internal processes such as supernova feedback. And so we conclusively say for at least this sample that there's no significant detection of environmental quenching. But then the next question that we have to ask is, when does this happen? Because we see at redshift 0 these galaxy clusters capable of driving tons and tons of galaxies to be quenched. And so what we want to see is our result just a function of environmental density would we see a potential signature of environmental quenching in denser environments? Or perhaps we need to go down to lower redshifts. And what this means is that we need to take more data to look for protoclusters with similarly well-sampled SEDs to continue conducting our analysis. And so I leave up my paper here for everyone, and I'm happy to take questions now. Thank you.
Question?
Okay, thank you for your interesting talk. So from your talk, I get that you were classifying the protocluster sample and the field sample using only the redshift distribution, so only in the 1D. But and then you found no like different in their environmental dependence. So I'm wondering whether you considered about also getting the protocluster sample from the 2D distribution, so combining those 1D redshift and the 2D too.
Yeah, so I think you want to see this photo, which is, are you talking about 2D as in spatially?
Yeah.
Okay, yeah, so when you look at it spatially, what you see on the left is the overdensity, and on the right is the field. There's not that much difference, and a lot of it has to do with the fact that we're in the lensing field. And so you have to look into the source plane, and what you see is that we don't probe that much area when you consider the magnification effect. So there's not really any significant distribution. And then if we look at it as a function of the distance from the nearest mass of quiescent galaxy, there's also no significant difference there as well.
I see, thank you.
Any other question? I have one. So you are currently focusing on low mass systems, but the star formation history, they are not different between clusters. If you do the same thing for massive ones, what happens?
Yeah, so I don't think I have that slide here. Yeah, I don't have that slide. Basically, the high mass and the intermediate mass, and there's no difference between the protocluster and the field as well. There is a redshift evolution where you see that the quenching times and formation times are higher, like earlier on in the universe, as we would expect with hierarchical modeling, or sorry, not hierarchical modeling, but hierarchical growth and like downsizing, but we don't see a difference between the protocluster and the field as well. Most likely due to the fact that they're internally being quenched via AGN feedback and whatnot.
Any other? No? Hey, so it's time to move on. Let's thank the speaker.